In the last episode, we learned about resilience, which is the ability of an AI agent to continue achieving its goals even when things go wrong. We learned about various techniques such as guardrails and validation that can be implemented to prevent failures in AI agents. However, despite diligent implementation of prevention techniques, there can still be some issues that are unavoidable. For example, you can get ambiguous user requests, or a model can hallucinate, API may be unavailable, or your network may time out. You may also have incomplete or inconsistent data from an external system. The real question, therefore, is not whether the failures will occur. The question becomes whether your agent has been designed to respond to those failures when they occur. In traditional systems, we often follow a fail fast philosophy. If something breaks, we return an error. However, with agentic systems, the expectation is that the agent will adapt, recover, and continue making progress like a human being. Think about a human employee. If some source of information is unavailable, they don't immediately stop working. They try another source. And if a task fails, they adjust their approach. If they need help, they ask for help. Resilient agents are also expected to behave in a similar manner. And in this presentation, we will discuss some popular techniques for resilient agents to recover from failures. When something goes wrong, the resilient agent is expected to follow a structured recovery process. It may simply retry the operation, and if it doesn't work, it can fall back to an alternate approach. If some progress was already made when the error happened, then the agent should be able to recover and continue from where it had left off. And when the situation is too risky or uncertain, it should be able to escalate to a human being for review or approval. Before we talk about different recovery techniques, it is important to recognize that not all failures are the same. For example, a temporary network timeout is very different from an API crashing. Each failure has a different root cause, and therefore it requires a different recovery strategy. So let us look at how you can classify the different anticipated errors for your business use case. Transient errors are temporary issues such as network timeouts, rate limits, or service overloads. These problems are usually short lived, and a simple retry is often enough to recover from them. Dependency failures happen when an external API, database, or a model is unavailable. In such situations, you can have a fallback strategy to switch to an alternate service or workflow if it is available. Execution errors happen when agent or tool fails while performing a task. For example, a workflow may crash or you may have an invalid output. The recovery techniques here may involve retries, validation, or alternate execution paths. Partial completion occurs when some portion of workflow steps succeed before the failure happens. In this case, rather than starting everything from the beginning, the agent typically starts from where they left off. Duplicate execution happens when the same action is performed multiple times, often due to retries. In such cases, it is important to implement idempotency techniques which ensure that repeated requests produce only a single business outcome and does not lead to duplicates in the system. And when situations are too risky or uncertain for agent to automate completely, then they must be able to escalate to a human for review and approval. So when you're designing your AI system, you must anticipate the kind of potential errors you can encounter. You should classify these errors as different types that we discussed and then use this decision flow to decide what kind of recovery mechanisms you need to implement. For example, if the errors are transient, then maybe you should implement a retry. And if there is an alternate path available, for example, another model that you can call or another API that you can call when the primary API is down, then maybe you should implement fallback mechanisms. When the workflow cannot be restarted from the beginning after failure, then you must implement the resume functionality in your code. And finally, you must identify the high risk and low confidence use cases that you should forward to a human for review. Let us learn the different recovery techniques that we discussed. For failures that are transient, such as a network timeout, overloaded API, or rate limit, which may disappear a few seconds later, retry is the simplest recovery mechanism. In resilient systems that retry intelligently, we implement exponential backoff, where we increase wait times between two consecutive retries. For example, if the first retry happened 1 second after the failure, then the next retry could happen 2 seconds after the last retry, and the next retry could happen 4 seconds after the last retry. So we continuously increase the wait time between different retries. We can also introduce a random jitter, which is basically some random time between the two retries. This can avoid multiple agents to keep hitting the service in a rhythm. And systems also enforce retry limits to prevent infinite loops of retry. For example, in this case, you can see we have a max attempt, which is the maximum number of times we can retry. And in this loop, you can see we have a delay, which we multiply by 2 every time to implement the exponential backoff. When retrying is not enough, the next strategy is to fall back on an alternate approach. For example, if a model endpoint is unavailable, or if you have exceeded your model quota for some time period, maybe you can have a different model endpoint that you can hit. Similarly, if you have a search API that is down, then you may have a complementary search service, which is a fallback mechanism that you can try. You can also use fallback mechanisms when your primary workflow fails for some reason. You can have simpler workflow execution that you can trigger. For example, if your primary workflow extracts multimodal data such as text and images from the documents, and the document that you received is poorly scanned, you can trigger a simpler workflow that extracts only text using the documents and ignores images. The goal here is that instead of failing the entire workflow, the output may contain less information, but workflow can still complete successfully. When retries or fallback mechanisms are not an option, and you must recover from the last successful state where failure happens, you must implement recovery techniques, which are checkpointing, idempotency, and compensating actions. So let's look at each one of these. Checkpointing is a technique where an agent periodically saves its execution state on permanent storage so that it can resume from that point if something fails. This is particularly useful for long running workflows that may execute dozens of steps across multiple systems. Restarting from the very beginning could be inefficient, expensive, or many times may not even be an option. Checkpointing allows the agent to resume from the last known good state rather than restarting the entire workflow. Besides persisting the workflow state, agents can also maintain a log of workflow events that it can replay to restore progress in case of failure. Modern agent frameworks such as LangGraph provide inbuilt features for durable execution capabilities that automatically persist workflow state. The next technique for implementing failure recovery is to implement compensating actions. Some actions cannot be simply rolled back. Once an email has been sent, a payment has been processed, or a reservation has been created, the action has already happened in the real world. In such situations, resilient systems use compensating action. A compensating action does not undo the history, instead, it performs another action that restores the system to a consistent state. If you are a technology professional who has built distributed systems, then you may be familiar with saga patterns, where every important action has a corresponding compensation step. A payment may have a refund operation, a reservation may have a cancellation operation, a ticket creation may have a ticket closure operation. For example, in this case, the travel agent booked the flight and charged the card when it encountered an error when booking the hotel. So, compensating actions are refunding the card, canceling the flight, and releasing the hotel hold. And the third technique for implementing failure recovery is to implement idempotency, which basically means that multiple retries of the same operation will produce a single outcome and will not create duplicates in the system. Idempotency can be one of the most important recovery mechanisms, especially when the agent works with external systems, databases, or APIs. Resilient agents are designed to retry operations, and without proper idempotency safeguards, these retries can create real problems such as duplicate payments, orders, tickets, records in the database, etc. Idempotency, however, is not an agent concern. It is a shared responsibility between the agent and the surrounding system that it interacts with. On the agent side, the responsibility is to preserve a stable identifier for a logical operation across retries. In other words, if the agent is retrying the same action, it needs to clearly signal that this is the same request as before. And on the system side, the responsibility is to recognize that identifier and ensure that the business action can happen only once. One of the most common ways to do this is using idempotency keys. The agent generates a unique identifier for a business operation, like a refund request in this case, and then it reuses the same key every time it retries the operation. The downstream service receives the request and checks whether the key has already been processed. If it has, it doesn't execute the action again. It simply returns the original result. Another approach to implement idempotency is to use stable business facts to identify if the business operation has happened. For example, when requesting refund for an order ID, the order ID can be used to identify if the refund was already issued. And some other ways system can enforce idempotency is to implement check before act logic, where you can check if a file or a database record or an entity exists in a system and either update it or ignore it because the business operation has already happened. And the final recovery strategy is to involve a human for review and approval. Sometimes an agent encounters situations where it cannot safely recover on its own. The retries may have failed, the fallback options may have exhausted, and agent may not have enough confidence to determine the next correct action. In such situations, the safest recovery path is to transfer the control to a human. The agent preserves its current state, provides the relevant context and evidence, and asks a human to resolve the case. For example, in this case, a payment which is over $1,000 was retried 3 times and it failed every time. It could be because the payment gateway has some issue, or it could also be that this particular payment has some issue that a human must review. For such situations, you can implement human review in your workflow process. To sum it all up, as a developer of an AI agent, you determine what kind of potential errors your AI agent can encounter. Then you classify them into different classifications, and depending upon the type of the error, you should implement a recovery mechanism. For example, for timeout or rate limit kind of errors, a retry is sufficient. When a tool or an external API is unavailable for an extended time, you can implement a fallback mechanism if possible. If the process was interrupted midway, then you should have mechanisms to resume from the last stable state. And if partial actions were completed and a system is in inconsistent state, then your agent should be able to implement compensating actions. For duplicate retries, agent and the surrounding systems should support idempotency. And for high risk, low confidence use cases where system cannot make a decision automatically, you must incorporate a human review in your AI agent workflow process.